Hi class, so this is going to be a lecture on continental drift, and then we'll get into the plate boundaries. You might not know what that is yet, but it will make sense hopefully after today. We previously talked about continental drift, so this ties in with that, but continental drift and plate tectonics are not the exact same thing, so hopefully that makes sense after today as well. So a little review on continental drift. This was an idea put forward by Alfred Wegener, and he said that he thought that the continents could move across the Earth's surface and that they once were together as a supercontinent called Pangaea. And now that we have more and more evidence, geologists have actually figured out that this has happened more than once, that the continents have gone around the globe, met up with each other, and then gone apart and met up again. So this has actually happened more than once. There was a supercontinent before Pangaea called Rodinia. So we have a lot of evidence that Alfred Wegener was correct with his theory of continental drift, but he was not received very positively at all by the scientific community. There were bits of people that agreed with him that had found similar evidence, but overall they said, "You're nuts. How could the continents move across the surface of the Earth?" So there was a gap in his theory. He didn't have any way to tell them how the continents could have moved. And so this is a pretty recent thing. Within the last 30 years, this has really become a very, very prominent theory of continental drift. And that's because we've learned so much about the movement of the inside of the Earth. But we'll get into that in a second. So most of the scientific community rejected Wegener's idea because he couldn't explain how the continents could have moved. My friend in Australia sent me this. So maybe this is really what's going on. I doubt it. It's just a joke, but it's extra funny because in general, Australians really hate cats. So there you go. So one of the big things that happened was Marie Tharp is a cartographer, and so that means she's making maps. And so there'll be a few videos on this that I would urge you to look up. Or maybe I'll provide the links, but she was a geologist and was in a lab with a bunch of people at Columbia. You can see out the window here, it's snowing outside in New York, and her colleagues would go sailing on the boat, and they would record this data of the bottom of the ocean. And so this was funded by the US Navy because we were trying to learn about where submarines might hide, or what the topography of the bottom of the ocean is so that our submarines could safely travel in the ocean. So they're trying to learn about the bottom of the sea, and I'll show you kind of how they do that. Let me find some markers here. All right, so let's stick this here. I don't have blue handy, so the surface of the ocean is green. So there's the surface of the ocean. Let's say that the bottom of the sea in this region has some undersea volcanoes or something like that. Like that. So this is a side view showing the surface of the ocean and the seafloor down here. And so they still do this today. It's actually using waves. They use sound waves and bounce the waves off the bottom of the ocean and see how long it takes the wave to return to the surface. So here's a little boat, little research boat, and it sends a sound wave down, and then that reflects back to a receiver, and they measure how long it takes that sound wave to bounce back. And so they'll travel, across the ocean, taking these measurements as they go. And so what they end up with is a table of data. And then the computers, at this point could do a very rudimentary job, not really computers, but kind of like a printout, and put together this data. And so Marie Tharp would actually put this data together by hand. She would get data on how long it took the sound wave to come back to the boat, and then convert that into distance to the seafloor, based on the speed. And then she would make these profiles of the seafloor that look like this. You can see some in the picture here. And so that's just a cross-section across the ocean. So then she would line up hundreds and hundreds of these cross-sections to make these huge maps of the ocean floor. So these are some of the cross-sections. Let me get a pen here so I can show you on the picture. These are some of the cross-sections that she would make and then line those up across the map, based on the location of where the boat went across the ocean, and then draw in, based on her interpretation, what the bottom of the ocean looked like. So this is extremely painstaking work. I'm sure she took probably 1 million hours over her lifetime to build these maps. And so this is one of her most famous maps, and you've probably seen it in a science classroom. And it shows the surface of the land, which was known at the time because people had, hiked around on the land, but it also showed the surface of the ocean. You can see this is the Pacific Ocean over here, this chain of islands right here, this is Hawaii. But then she found, there's actually more under the ocean volcanoes that are part of the Hawaiian chain. There's a ton of volcanoes out here on the bottom of the ocean. There's a lot of flat regions on the bottom of the sea, and then there's these mountain ranges that go all around the earth and connect. This one goes like this, like this. Before this research, they thought that the ocean floor was pretty flat and boring, but she proved that this is not the case. And so they found these features that went all around the world, and they were in a side view, like a very prominent ridge in the middle of the ocean. This is showing this mountain range here. And so she called these mid-ocean ridges, and this ended up being a huge step forward for science and helped to give a mechanism for how Alfred Wegener's continental drift theory, how that could have worked with the continents moving. So, without further ado, here's a really cool little graphic. She says, I was so busy making maps, I let the guys argue, because everyone was arguing about what she found. But she was, sticking to her guns and just kept plugging away. She said, there's a truth to the old cliche that a picture is worth 1,000 words, and seeing is believing. So she made the first map of the ocean floor. Pretty amazing. And she made maps all over the place. Amazing amount of work put into that. So this is a piece of one of her maps, and you can see North America over here and Europe here. So this is the Atlantic Ocean, and you see this feature that runs down. This is the mid-ocean ridge that she found. This is a place we're going to discuss a little later called Iceland, which is an island that's actually along the mid-ocean ridge. So part of the mid-ocean ridge sticks up above the ocean. So this was recognized as a feature that people, believed in. They actually, Jacques Cousteau took videos of the ocean floor thinking he was going to find that flat, boring surface. He actually found these ridges as well with his videos. So that kind of shocked the scientific community. So after this, there's been a lot of geophysical research done. And so this is research of the interior of the Earth. We discussed how you can use waves to penetrate the Earth and learn about the different layers. But they've also learned a lot about how the inside of the Earth, different parts of it that are somewhat fluid, are moving. And so now they've figured out that there's two different large ways that the continental plates are moving, the continents are moving. There's ridge push and slab pull. Ridge push has to do with magma. If you have rock that's melted, it's less dense, so it tends to rise up over time. And so that pushes toward the surface of Earth, and that'll thin the crust in that location. And that'll kind of start a mid-ocean ridge location where the crust is pushed up and thinned. And when it's pushed up, the crust is pushed up, then gravity is going to pull those pieces apart. So it's going to start to open up a piece of the crust, essentially. And then at the edges of the crust plates, so this is kind of showing different plates of the crust, the weight of the plates pulling apart after a while, so my elbows are the edges, pulls the edges of the plates apart and opens that up as a mid-ocean ridge. And so one thing that's important that I should have talked about earlier is that we now know that the crust is not one piece. It's made up of different plates that move relative to each other. And so that's what I was trying to show with my arms moving apart. So therefore, we talked about the interior layers of the Earth. What would you say is the ultimate cause of plate tectonics then? Plate tectonics is the theory that pieces of the Earth's crust are different plates, different pieces that move relative to one another. So what is the cause of this movement? Is it heat transfer away from Earth's interior? Lunar and solar tides? We haven't really linked it with tides, so I wouldn't say that. Is the ultimate cause the seafloor spreading itself or the continental drift? So I would say it's heat transfer from the Earth's interior, because that's what causes seafloor spreading, which is what causes continental drift. So I would go with A on this one. And here's an explanation. Feel free to pause and read this. So continental drift needed an explanation. Seafloor spreading helps, but they need evidence that it's actually moving apart. So we can see the ridges on the surface of the Earth. So if the middle of the ocean was breaking apart, you'd expect to see these ridges, right? This shape that Marie Tharp found with the ridges like this, if they were pulling apart. But we don't have evidence at this point. We didn't have evidence that they were actually moving. We didn't have GPS. We had no way of measuring the movement of the continents. So there's still work that had to be done. One thing was paleomagnetism, and so the Earth obviously has a magnetic field because we can take our compass outside or inside, it doesn't matter where you are. You can take a compass and see that it aligns north if you have magnetic minerals in your compass. And so we have a magnetic field where north is somewhat at the North Pole and somewhat at the South Pole. It's a little tilted relative to what you might think. But in the past, there's actually been many different reversals where the magnetic field of the Earth has switched, and so your compass in the past would have pointed towards what we think of as the South Pole, but that would have been the magnetic North Pole at the time. So this is an image that shows a reversed magnetism with the South Pole up here, North Pole down here. So the interior of the Earth, actually the outer core, is made of liquid metal that moves. And so that moves over time, and when that moves in a particular orientation, that causes the reversal of magnetic poles. So that's happened back and forth hundreds of times in Earth's history. So we can actually look at the minerals in the layers of ocean crust, and there's evidence for this ocean crust spreading. So as the plates are moving apart at the mid-ocean ridge, there's new lava coming out, and that's forming brand new ocean crust igneous rocks. It's mostly forming this rock basalt, which is kind of a boring looking rock, but it's a very heavy, has lots of mafic minerals. So this is mostly what's making up the bottom of the ocean crust. And so when that magma comes out, this is showing the beginning, when the magma first comes out, it hardens into the crust, so it hardens into this rock basalt. This has lots of iron minerals in it. That's why it's so heavy. And those iron minerals lock in whatever the magnetic polarity is at that moment. So it's like it has tiny magnets built into the minerals themselves in the rock. And so that locks in the polarity at that moment, And so you'll see the same polarity on each side of the mid-ocean ridge because the magma comes out pretty evenly on both sides. And so then over time you might have, this is showing normal polarity with the colors and reversed with the white areas. So over time you might have an area that comes out during a reversal, some lava that comes out during a reversal, so you'll get that banding pattern on either side of the mid-ocean ridge. And then you might have normal polarity for a while, and then some of this magma come out and harden into rock on either side of the ridge. Then here we've got the white, the reversed polarity, and then the red normal polarity. So it reverses, but we see this pattern being very symmetrical on either side of the mid-ocean ridge. And unfortunately, it's not color-coded. You have to actually drill down into the ocean crust and take a sample and take it back to the lab to analyze it for polarity. I've actually done that to date rocks in the past, which is kind of an interesting way to date rocks. You can use that instead of isotopes sometimes. So the other thing to notice about this is that means that the rocks that are, let me erase all my crazy sketching here and find a new color. How about green? So that means that the rocks that are closest to the mid-ocean ridge, right here, I'm up at the top now, these are the youngest rocks because they get pushed away from the ridge over time by new rock coming out and forming. So that means the youngest rocks are right along the mid-ocean ridge and the oldest rocks are farthest away. So right off the coast of North Carolina, that's where I'm from, that's obviously, by the continent is the oldest ocean crust that you have, and so that's some of the oldest ocean rock that you'll find in the world. It's right off North Carolina because it's far from the middle of the sea. Cool. So how does plate tectonics differ from continental drift? I'm going to actually let you read these. So I would go with this first one. Plate tectonics provides a credible driving force. That means a way for continental drift to have happened. So here I told you that the crust is broken up into multiple plates, pieces that move relative to one another. This is a map of some of these major plate boundaries, and here's North America. Let me find brighter color to show you. Here's North America, so we're on the North American plate, so that's easy to remember. But it's interesting because we can't look from space and see this. So how do we get this information about where the edges of the plates are? They're covered up with soil and trees just like everything else. We can't just see these. How do we know, where the mid-ocean ridges are? So for the mid-ocean ridges, we know this because of the work of Marie Tharp and her colleagues and all the mapping of the ocean floor that we've done. But additionally, we can use the locations of earthquakes and volcanoes. So in this image, let me switch my color here. The little red dots represent locations of earthquakes. Here's some, in North America. And then the little triangles, little black triangles, are showing the locations of volcanoes. And so you can see that the mid-ocean ridge is outlined by earthquake activity and some volcanoes as well. And the edges of the plates is where there's lots of this earthquake and volcano activity. And so that's actually how we've defined the edges of the crust. It's always being refined. Science is always changing what we have evidence for. But, as we get new data and everything. But this is our best guess of where the edges of the continents are because of where the earthquakes and volcanoes are. So earthquakes and volcanoes are usually caused by tectonic movement along the edges of the crust. So we'll talk about that in a little bit. So there's two major types of crust that we've already discussed a little bit. There's oceanic crust. Let me grab a brighter color. Oceanic crust is mostly formed of this rock basalt. I have two samples here. This dark rock, you can't see the crystals because it forms really quickly at the surface and it cools quickly. This is an example of an extrusive igneous rock. So this is very dense and heavy. And so this causes the ocean crust to be extremely heavy and sink down into the mantle a little bit. And so if you have an area of the Earth's surface that sinks down a little bit, that's going to make a low spot. And as we know from puddles in our yard, a low spot is going to collect water. So that's essentially why the oceans are where they are, which I think is crazy. It's because the crust in those locations is denser, so it sinks down a little bit, and it makes that basin that's then filled up with water. The continental crust, on the other hand, is usually thicker crust, but it's also lighter weight. It's also lighter in color, so that's easy to remember. This is an example of granite, which is a different type of igneous rock. This is intrusive, usually forms underground. Well, it always forms underground. You can see the crystals in it. See the different colors, black and pink and gray and white. So granite's an intrusive rock. This one's almost completely pink, but you can't see the crystals in it. So if we drill down anywhere we are on a continent, pretty much we can find granite, which is cool to think about. It's usually covered up by sedimentary rock layers. That's usually what we see on the side of the road or something like that. But if we drill deep enough, we'll find it. So major types of plate boundaries, this is talking about where tectonic plates run into each other or interact with each other. It depends on which type of crust you have running into each other. So we're going to discuss some examples. The three main kinds are divergent. So this is where the crust, the tectonic plates are moving apart. Convergent is where the tectonic plates are moving together, so they're running into each other. And transform is when they're running sideways into each other like this. So we're going to discuss these different examples. Divergent plate boundaries, the biggest example is, of course, this mid-ocean ridge. It goes all around the world. But there's one place we can actually observe it above the surface, and that's in Iceland. So this is between North America and Europe, but it's up here. It's pretty cold. This is a location in Iceland where you can actually scuba dive inside the mid-ocean ridge. This is a scuba diver right here, and this is the surface up here of a lake that's in Iceland. So this is a mid-ocean ridge. You see how clear the water is in this lake. I think that'd be a pretty cool place to scuba dive inside the ridge. Usually the ridge is about 3 miles deep under the ocean, but in this location in Iceland, there's been so much lava rock built up, so much igneous rock built up. It's actually made an island, and that's the island of Iceland. There's lots of volcanoes, and so all this rock along the side here is this basalt. So pretty cool. So that's one reason Iceland's a big location for photographers. It has a lot of volcanoes. Those are photogenic. It also has a lot of ridges and places where the Earth's crust has been pushed up in different ways and pulled apart. So it has a lot of valleys and cliffs, and the cliffs make a lot of nice waterfalls. So if you like photography, I would look up pictures of Iceland. It's a very spectacular place. So here's a little map of Iceland showing the mid-ocean ridge running right through. And these are some of the volcanoes. These little red triangles are showing the active volcanoes. This was also showing the movement of the different plates moving apart. So in a divergent boundary, the plates are being pulled apart. So that was an example of, mid-ocean ridge is an example of ocean crust being pulled apart. So down here is a side view of the Atlantic Ocean and the mid-ocean ridge in the center at the very bottom of this image. But there's a couple other interesting things. You can have the Colorado Plateau is a continental example up at the top of this image, where the continent is having some pushing from magma underneath and it's starting to crack the crust and weaken it. And so this is kind of like the beginning of, it's potentially the beginning of the formation of a mid-ocean ridge. That's also true in the East African Rift Valley. If you've ever heard of Lake Victoria and Victoria Falls, that's actually on a rift valley, so that's the location where the crust is weakening and cracking, and the continental crust is actually starting to move apart. And so the middle parts of the crust are falling in as it cracks apart. The Red Sea is a location where a mid-ocean ridge is just starting to form because of rifting. Rifting is when the crust is starting to crack and pieces are falling in. So there's a few different examples of divergent boundaries. And here's a map showing where some of these locations are. This is Africa up at the top right corner, and it shows the East African Rift, and that's this area here with Lake Victoria, Victoria Falls. Mount Kilimanjaro is also in this location, so there's lots of volcanic activity at these types of locations. Obviously, we know where the mid-ocean ridge is, and the Gulf of California is another weird example of some rifting and moving apart of plates. But the mid-ocean ridges are, of course, the largest divergent plate boundaries and also the largest mountain ranges that are found on Earth. The mid-ocean ridges also have really interesting biology and interesting features where they have this stuff called white smoke coming out. So this is the rock over here. This is a picture taken by basically a submarine at the bottom of the ocean. But what happens is that the bottom of the ocean has the densest, coldest water, of course, because it's at the bottom. And then that sinks into little cracks and crevices in the crust, in the rock. And so it sinks down in, and it kind of becomes part of the rock. I mean, if you had a rock sitting at the bottom of the ocean for thousands of years, it would be very wet, right? So then the water is down in there, and it starts sinking down and down and down, but it's interacting with the magma chamber, because remember at the mid-ocean ridge, the lava is coming out, so that means the magma chamber is right underneath the surface. So it's interacting with that, getting superheated, and so some of the minerals in the crust dissolve and get into the water. So that'd be really weird tasting water, probably pretty dangerous to drink. But it gets into the water and it heats it up and it shoots it out as it gets really hot, and it starts to boil and it shoots it out of these features called white smokers and black smokers. You can see some black smoke coming out down here. And the color of the minerals coming out is just based on whatever's dissolved at that location. So that's putting a lot of interesting chemistry into the water. It's actually one way that salts get into the water to make the ocean salty. Additionally, this heat, it has a lot of compounds that different animals can use. And so a lot of these creatures that live at the bottom of the mid-ocean ridge use the chemicals that come out as the base of their food chain. Instead of using sunlight, they're actually using chemicals that come out of the smokers at the mid-ocean ridge to have their food chain. So there's a lot of different crabs, and some of these tube worms are like 10 feet long. They can get really big because they have a lot of energy coming out. The next one we're going to talk about is convergent boundaries. And so this, of course, depends on the type of crust involved. So we'll do a couple examples. In this example, you've got continental crust running into continental crust. And one big example of this is the continent of India used to be its own piece, actually. And then it ran into the continent of Asia So if you had these two granites running into each other, they would be fighting because they have the same density. So it would be a very messy collision. But eventually one of the crusts would have to be denser than the other and eventually go underneath. But it would be a battle. So a location where you have continental crust running into continental crust usually forms a mountain range because there's so much pressure and pushing, and it pushes the crust up. So this is a picture from a satellite, and you see this huge mountain range. This is the Himalayas. So the Himalayan mountains were formed because over here is India was traveling north, crashing into the continent of Asia. Oh, pardon me. And so eventually the Indian plate was starting to subduct underneath the Asian plate, but there was a lot of pushing involved. It's a lot of mountain building. If you have a location where you have ocean crust running into ocean crust, you'll have a similar thing, but both of these crusts are pretty dense. So the one that's older, that's been at the bottom of the sea longest, is usually the coldest. So it's usually the densest one, so it would eventually push up underneath. But it kind of drags pieces of the ocean crust on top down with it. So you form this big trench. So this is a feature that's formed from ocean crust to ocean crust collisions. And we talked about how the water would be percolating down into the rock, filling up every little crack and crevice. So, and also there's lots of sediment on the surface of an ocean crust. There's lots of sand and mud and little bits of fossils and everything on the surface. So when this plate is subducted underneath, it has all this sedimentary material on top and water. And that means that this is not just pure basalt. It's basalt with stuff on top. And the stuff on top is going to melt pretty easily when it starts to be dragged down into the mantle. And so that's what's going to form some of this magma right here. So as the crust goes down into the earth and gets heated up, this stuff that was on top starts to melt the rock. So the basalt and also the stuff on top, we can think about it as frosting on a cake. That stuff is going to start to melt. So that's going to cause magma. The magma is less dense than the surrounding rock, so it starts to rise up and form volcanoes. So a lot of times at these locations you find volcanoes forming, but this is under the ocean. And eventually these volcanoes might come to the surface and grow big enough to come up to the surface. So there's a lot of volcanoes under the ocean that we don't even see, but sometimes they come to the surface and form islands. So this is an example of the Pacific Ocean. Here's the North America over here. And so the Hawaiian Islands are here, and that's a whole different thing. But we see these chains of volcanoes all around like this. So this is Alaska. These are the Aleutian Islands that come off of Alaska. These are formed by this process right on the edge of the ocean crust. Let me get yellow. So you see this really dark line along here? That's showing the trench along the plate boundary. So there's this trench, and then right behind it are these volcanoes forming. So we've got the Aleutian Islands of Alaska. We've also got the islands of Japan over here on the left. So those are some examples of these islands formed by plate boundaries. A similar process happens if an ocean crust runs into a continental crust. But which of these is going to go underneath? Which one is denser? So the basalt of the ocean crust is denser, so it's going to go up underneath the continental crust. So that's exactly what happens. The ocean crust ends up going underneath the continental crust. But similarly, it has all that stuff on it. It melts easily as it goes down, forms magma, comes up, forms volcanoes. So then we end up with volcanoes on the continent. So that's even more dangerous for people usually. So here's some examples. Up in the northwest US, you've got volcanoes such as Mount St. Helens. That was formed in this way. And also the Andes Mountains down in South America were formed in this way as well, from ocean crust going underneath continental crust. There's actually now we've given many examples of how the Pacific Ocean is just surrounded by volcanoes. So in the top image here, these little triangles are showing volcanoes. So the Pacific Ocean has volcanoes all around it. This is the Pacific Ocean here. So that's often called the Ring of Fire because it has so many volcanoes. Earthquakes are also formed a lot at tectonic plate boundaries. Because think of how much energy there would be if an entire piece of the crust that's several miles thick is running into another piece of crust. That would be a location with a lot of friction and a lot of pressure on the rocks, and an earthquake is formed when a faulting occurs when the rock cracks and moves. And so that would happen a lot at plate boundaries as well. And the last one we're going to talk about is transform plate boundaries. And this one, there's not a lot of vertical movement. There's not going to be a plate going under the other. Instead, they're going to move past each other. But there's always a bit of, weirdness. So there's also a lot of friction involved in this, so a lot of earthquakes occur at transform boundaries. The most famous transform boundary in North America is the San Andreas fault system. This is actually several different faults, but we've got this plate moving kind of towards the north, and the North American plate moving kind of towards the south. There's lots of pushing going on sideways. So that's why they have so many earthquakes over in California. This is an image from the sky, and you can see this fault right here, and that there's a river kind of running through it here. So this is an example of one of the fault systems at the San Andreas fault zone. So here's some kind of review questions to go over these different types of boundaries. So I'll just go through these a little bit, I guess. At which type of plate boundary is new lithosphere created? So lithosphere is kind of a fancy word for the crust. So where is new crust being created? Where is new rock forming? And this would be at divergent boundaries, where you have the lava coming up and forming new rock, such as a mid-ocean ridge. Let me change my color. Divergent boundaries. Which type of plate boundary is the crust, the lithosphere, neither created or destroyed? So what would an example be of destroying it? What if the crust goes under the other crust and gets melted inside the earth? That would destroy the crust. So we don't want that one. We don't want the one where new crust is being formed. So how about a transform fault boundary? This is pretty much the crust just moving sideways. So it's not getting created or destroyed. Subduction happens at which plate boundary? So subduction is that process of one plate moving underneath the other one. It's getting subducted. So that would be a convergent plate boundary.